Hi all, welcome to another session from Nado Research. I'm Srijit here, and in this session, I'm going to brief you about machine learning potentials in AMS, Amsterdam Modelling Suite. So, speaking about MLP, it provides a powerful way to model large, complex material systems within near DFT accuracy at a fraction of the computation cost. They are especially valuable in battery materials, catalysis, and material discovery, where long molecular dynamic simulations and large supersets are required. So, what are MLPs in AMS? So, speaking about MLPs, they are basically data-driven interatomic potential strains on quantum mechanical reference data, usually DFT energies, forces, and stress. Once trained, they can replace direct DFT calculations in MD or geometry optimization, enabling simulations of thousands to millions of atoms over nanosecond time scales. In AMS, MLB are tightly integrated into the standard workflow, allowing seamless switching between DFT, ML, and classical force fields. So this is actually the interface of MLP in AMS GUI, where you can see the various models. So right now I'm using this M3GNet Universal Potential 2022 for our calculations, where we are performing typical nudge elastic band calculation starting with the geometry optimization. So we will be discussing that in the later sessions. So here I'm just giving you an intro. So here this optimization is performed with the lattice optimization. So I'll brief everything step by step. So machine learning potential frameworks supported in AMS, so which supports several state of art of ML potential approaches, including neural network potentials or NNPs, which captures complex many-body interaction with high accuracy suitable for chemically diverse systems, and then Gaussian approximation potentials with uses smooth overlap of atomic positions, descriptors widely applied in material science. Then MTP, efficient and accurate for crystalline solids and alloys, ideal for lattice dominated systems. So these potentials can be trained using ADF for band DFT data and then deployed directly to the MS simulations. So that we will discuss in the upcoming sessions. Then how we can train ML potentials in AMS. So AMS provides tools to generate reference datasets from DFT calculations, train ML models using energies, volts, and stress. It will validate accuracy against the test structures. So training workflows often involve active learning, where the ML potential improves by identifying configurations where the predictions are uncertain and adding them to the training set. So this is particularly effective for battery materials undergoing phase transition, diffusion events, and lattice distortion. So that we will discuss in the upcoming session. So applications in battery and material modeling. So that is one of the most important example I'm going to brief in the coming sessions. In battery research, ML potentials enable the long time scale ion diffusion simulations, thermal stability and degradation studies, a large supercell geometry optimization with the lattice relaxation. So this is actually an example which I have already executed with MLP, and mechanical property calculations under strain. So they bridge a gap between the DFT accuracy and classical NB efficiency, making realistic battery simulation feasible. So the integration with AMS workflow. So MLPs in AMS can be used for geometry optimization, fixed load relaxed lattice, molecular dynamics like NBT, phonon and vibration analysis, stress, strain, and elastic constant calculations, because they are embedded within AMS results that can be analyzed using the same GUI tools as DFT or React server, ensuring consistency across multi-scale workflows. So, as a summary, machine learning potentials in AMS combine accuracy, efficiency, and scalability, enabling simulations they are impractical with pure DFT. So, for researchers like us, while working in battery materials and solid-state modeling, they can provide an essential pathway in study the realistic systems while retaining a strong connection to first principle physics. So this is actually a basic introduction about MLPs, and this is actually one calculation which I have already performed. So let me show you that what is the official outcome of this geometry optimization. So let me go to this AMS movie, and I will show you that what is actually the animation of this specific system. So you can see while running this, so how that optimization progresses with the energy as well as the mass stress energy per atom. So this is actually the overview about this MLP, and also a simple geometry optimization using ML. Okay, so in the next session, we will be continuing with the more examples covering up the battery modeling material, that how we can undergo ionic migration or ionic diffusion in a battery material. So thank you. We'll see you in the next session.